The first time I saw it, I'm like, wait, does this mean 10 is built into reality? No, that can't be the case. That can't be the case. It kind of looks like it may be the case.
You finally flipped.
I've heard that as we go to update different things and we go to adjust different constants, one of the things I learned from that is some of the constants we saw upwards of about a 3.5 sigma swing. And it can be really hard because you have all these different smart folks from all these different fields, and they're working really hard and they're trying to get the best estimates that they can. But a lot of folks there spend all their time in their field. They spend all their time working on their things that are important to them because they are important. The only issue that can run into is if you might have the best calculation that you have to your knowledge and the limits of our technology within your field. However, if you're trying to align everything up, like, what was it? I think we were on Wolfram Alpha earlier, and we took a look at the atomic mass units. They have the atomic mass unit, but depending on which one you click on, like, okay, the physics one, okay, it's good for about the first 4 or so significant digits. And then you have the chemistry one, and then it's good for the, and you go through and it's like, well, these are different. These don't seem to be quite as unified as, at least I would personally hope. And again, I'm not a professionally trained physicist. I'm just a guy that's trying to figure out things that's been very blessed in my life. Now, what we're looking for is, the whole point of the metric system is to have a coherent system of units. And that's one of the reasons why we've chosen to use this system for modeling the physical world, to maintain coherence. And one of the really cool things, and this is something that I've still been trying to wrap my head around, and it just seems to almost make the mind wobble, is that Thad managed to find some solutions for these things, and the solutions are very interesting. And I think it's at least worth sharing because it might help some folks. And again, I'm not going to say it's right or anything, but it provides maybe a clue for other smart folks out there to try to figure out what's going on, or maybe just even help them with some calculations. Give it a try. Hey, if it doesn't work and it ain't your thing, no worries. You don't got to use it. Just something that we're putting out there just so the world can try to, I would say level up, but I'm wearing the other shirt right now. But, okay, so one of the solutions here for, I like how you put them in the book, for the atomic mass constant. So it could also known as the atomic mass unit, the AMU, or sometimes the Dalton, depending on context. Okay, and we can write the A mass. So we'll do A mass because I am from Massachusetts, and it actually has maybe not all that surprising, actually similar construction to what we have for our Planck units there. And we can phrase that as 18 over 32, and then multiplied by pop, our universal parabolic constants. And then that's over J1 to the 6th power. So this is our primary reaction. Our boundary condition is the mass of the electron. That's pretty cool. That seems to be a very elementary unit that basing it off something off of probably not a bad idea. And we have our internal action, which is just 1 plus 1 over the lemniscate. And that's just multiplied by J1 minus J2. And then we multiply just by our inversion boundary box there. Okay. Okay, so, okay, yeah, you just search for something like that. I mean, it's kind of neat. We're saying that we're working in a theory utilizing derangements, so the ways you can arrange different things. 18 happens to correspond with the charge boundary, 32 with the temperature boundary. Okay, that's kind of neat. And then you look at the solution that had found for the kilogram. I thought it was pretty interesting. So if we just do kg, we can set that equal to, again, similar setup. This is 32 over 18. Je 1 to the 6 over the universal parabolic constant there. And then I think it should only be kilograms that, just because they're adding it to it in there. And when you do a computational, you know, it's going to the kids. But you basically you can do 1 over the mass of the electron in this case if you want to balance out dimensions, because they're looking for the ratio of like the kilogram in AMUs. It would be actually the unit of the kg. All right, so we'll do kilogram. Yes, we're putting the kilogram in the kilogram. I realize it's a little ironic, but over the mass of the electron. And then you do 1 minus 1 over the lemniscate. Je1 minus Je2 times our inversion boundary right there. Make that a little less abysmal. Okay. All right. So what the heck just happened?
Kilogram on the left hand side is just 1. And the mass is what?
It's the atomic mass unit. This is in ratio. We're utilizing the mass of the electron, which I'll put in the calculated notebook attached to the video. We're using the mass of the electron as our boundary condition. So this is our primary action, our boundary condition, and this is our inner, or we had called it the terminal action here, and it's the inversion over here. When you look, it's kind of just it is an inversion. It's like, all right, we put the 18 on the bottom, the 32 on top. We put the Je1 to the 6 from the bottom onto the top, and the universal parabolic constant from the top to the bottom. And then basically we just did 1 over the electron. We did this for computational purposes to cancel out the dimensions. And then you just go from 1 plus to 1 minus, same action. I'm not an expert, but there seems to be some symmetry going on there. But that's up for you all to decide for yourselves. I can't convince you of anything. I'm just sharing stuff that I found interesting. And when you look at the sigma on this, I believe it's 0. The sigma on this, if you actually go out with a few more digits, it's like 0.023% or 3% or something like that. And I'm like, I heard some folks saying that maybe something was it seemed a little off when they redefined the AMU and the kilogram with some of the updates. I have no idea what's going on. I can't verify it at all. I know there's a little note in like the Wikipedia article saying some folks disagree because it used to be just based upon carbon-12, 1/12 of carbon-12. Boom, there we go. But this is very interesting because if this is true, which we're going to have to see, this would imply there's very direct symmetry between the atomic mass unit and the kilogram, and it almost may help to explain why powers of 10 works so really dang well. And when you verify, this is verified, at least according to Wolfram Alpha, only deviation with what Wolfram Alpha has is in like the 14th significant digit and goes from like 9999 to like an 8 or something like that. So there's some deviation, full disclosure, whatever the reason for that deviation might be. I guess we're going to have to wait, see, and learn some more and do some more experiments. But that's all I really had for a quick little rundown of some of the constants. Yes, sir?
So the atomic mass number is 1.6 something. I looked it up just now.
Yeah.
The kilogram is just 1.
The kilogram in relation to the kilogram. Because the kilogram is 1, because the original way that had this was 1 over the mass of the electron to get out the dimensions of kilograms, because the mass of the electron we express in kilograms. But this is actually a relationship. This is kg in They express it U, which is basically just the atomic mass unit or the Dalton. Because I just tried it as that, and you won't get that. In order to actually get the actual numbers to compute, you need to have it expressed as kg times the atomic mass unit in there. So that's its reference.
The digits are one. The digit is not one.
No,
It's a number.
yeah, it's a number.
Yes, because the kilogram reference, that's why the quick hack, so to speak, is if you need to adjust the dimensions, they're just kilogram, meter, or something, because those are our reference ones for the system.
Yeah, it's a bit confusing because they use kg for the symbol of the constant, but the
So
full
it's
thing
not
is
kilogram, it's
kg.
kg.
It's kg in use.
Yes, kg expressed in this particular unit. And then when you multiply it, that's how you end up seeing the inversion here, because it ends up being a translation between the two of them, which, I mean, the first time I saw it, I'm like, wait, does this mean 10 is built into reality? No, that can't be the case. That can't be the case. It kind of looks like it may be the case. I don't know. But other than that, it's just very fascinating that you can utilize some algebraic geometry like this, and you can get what looks like a pretty
Serious symmetry.
some real serious symmetry going on there with the atomic mass unit and the kilogram. Also, when we utilize the atomic mass unit as our boundary condition, I think in like the proton, the neutron, it actually helps simplify things a lot. So, is it built into reality? Well, if we think we're real, this seems to be part of reality, or at least a mathematical, pretty good approximation, I would say. Anything else? Alex? Dad? Good? All right. Chicken time then. Cool. Thank you.
Thank you very much.
See the past through a flashback, back to the days when I didn't have rap, but nowadays, bitch, I'm all about that.